Good morning all of you. Welcome back to laser technology sessions. So in the previous classes we have discussed about the Gaussian beam and their properties and what are the parameters in the Gaussian beams. We discussed regarding the complete picture of the Gaussian beams. So today we are going to discuss about optical resonators, or also you can call laser resonators or cavities. So the optical resonators is analogy for the electrical resonators. So the similar the functioning and the amplification and the feedback system as we discussed in our previous classes. So this confines the light inside the cavity or the resonator and also stores the light at certain resonant frequencies. So that means it allows certain frequencies to resonate under the cavity. So we consider now some simple resonator systems. So using two plane mirrors you can construct a resonator. So this you can also call a Fabray-Perrot resonators. If you have like you can construct with the two glass plates in the similar functionality, you will get the Fabray-Perrot. Okay, so now using two plane mirrors you can construct a resonator, and you can use a spherical mirrors you can construct a resonator. And the major difference between the second and third, there is a distance, how far it is. Okay, so that decides the different resonating frequencies. Okay, and the other one we can construct using plane mirror and the spherical mirror. So these kind of combinations you can play with to construct a resonator. And today we will see, is it possible like all the resonators configurations can give a stable resonators. So we will discuss what are the stable resonators and what are the unstable resonators in the down the line. So this resonator determines the frequency and the spatial distribution of the laser beam. So from your longitudinal waves you will get the frequency, and from the spatial distribution, so that is along your radial distances, so you will get the spatial mode of your laser. That's what we see, the TM00 and the higher order modes. So now is a simple resonator is a plane wave like plane mirrors. So now what happens, you have any gain medium inside, so then you have lasing. So whatever the light incident on the mirror, again it reflects on the same line. So because you place such a way that both are perpendicular to each other, if you place any angle, so there is any misalignment in the angle, so now what happens, you have come up with a little instant angles, then they will resonate and they will the light will be escaped. So you have to be careful so that these both mirrors has to be perpendicular to each other. Okay, so you should not, the light should be incident perpendicularly so that it will be oscillate within the cavity. So the cavity of length L, so we know that the radius of the curvature of the plane mirror is infinity, and similarly your R1 and R2, your two mirrors are plane mirrors, your R1 and R2 will be infinity. Now we consider the second type. So in this, these are spherical mirrors. So now whatever the light incident on, so this mirror will try to focus on this mirror and this mirror will be try to focus on this mirror. That means we designed a cavity with your R1 of the mirror is equals to R2. So both of the mirrors having same radius of curvature, and that is equals to the distance apart. So that means the distance between these two mirrors. So for example, now the distance between these two mirrors you can measure like this. So this distance is L So now this design of this cavity is the radius of curvature of these mirrors is equals to the distance between the two mirrors. In that condition, you achieve a confocal configuration. So now your beam width will be smaller within the cavity at this position. So that means you have to assume that for the combination of these two mirrors, the focus will be here. Individual focus will be different, but when you compare the system, like or your resonator focus is at the center. So that means the focus will be shared by the system. These two mirrors will share the focus, shared focus will be at the center. So that kind of a system or configuration you call confocal configuration. And the other one, the third one, you have the mirrors, the same spherical mirrors used in the second. So now they are displaced such a way that your R1 equals to R2, that equals to L by 2. Okay, your radius of the curvatures of mirror 1 and mirror 2 is designed such a way that the radius of curvature is equals to L by 2. So that means they were going to focus at the center of your cavity. So that means all the light will be concentrated at the center. So this configuration we call concentric configuration. And the fourth one, as we are considering a simple resonator systems, the fourth one here is you have a plane mirror and you have one spherical mirror. So now the spherical mirror try to focus on the mirror M1, and this mirror M1 is a plane mirror. So what happens, it exactly reflects back whatever the light incident on the same angles from your reflection Snell's law. So you know that whatever the angle of incidence, if you want the plane mirror, it will be the angle of reflection will be the same. So now if angle is like this, then it reflects like this. If it is incident perpendicularly, then it will reflect back perpendicularly. So that means whatever the direction the light input gives, the reflection angle also will be same, so that you can get the exactly the light will reflect back to this spherical mirror. So now the radius of curvature for these two, the R1 equals to infinity and your R2 equals to L. So L is your length of the resonator. Okay, so in now we will always try to focus on a Gaussian mode, because many practical usages the Gaussian mode is the main priority. So now we will discuss about how do the Gaussian mode can be sustained in this kind of resonators. So now we take a confocal resonator. So confocal resonator, we know that the focus will be shared by this, the shared focus will be at the center. Okay, so your R1 and R2 is designed such a way that both are separated by distance L. So that is R1 R2 will be a cavity length. So you design your cavity, your mirrors such that whatever the cavity length, that is exactly matches with your radius of curvature R1 and R2. So L is the length separated by the two mirrors, or you can call it cavity length. Now if you see, these are the wavefronts. As the light reflect back from the mirror M1, your wavefronts follows the fashion like this. So now this is try to get your plane wavefronts at the center, because as I mentioned, your shade focus will be at the center of this resonator. So now again after the center, it will again having a curvature. So this is the wavefront or phase fronts. In principle we can call these are a phase fronts. So now your phase is almost like constant phase in this case. Now here you have a phase variation will be there, but that is a variation will be can be is a certain phase variation to one to the other point. Okay, so now if you have a beam, so now this is your, in principle, that is the light is try to get the minimum spot size at the center. Now if you see at the center, so you have a plane wave, so that means the phase is a constant. Now this is your, if you see this wavefront curvatures at the focus is infinity, so the curvature is infinity. As you go towards the mirror side, you will get the curvature of the mirror. It should be curvature of the mirror. So at this position, the wavefront curvature will be equals to your mirror curvature. Okay, so that is the propagation direction of the laser beam if we have amplifying medium. Okay, so now we already discussed about the Gaussian beam conditions. So this is your beam width radius, that is W naught, and this whole thing will be beam width W to W naught. The beam widths at the both mirrors should be small compared to mirror sizes for resonating a Gaussian mode. So that means now the beam width is larger, so then what happens, if the light will escape from these mirrors, so then what happens, you leak the light. That is one thing. The second thing, now what we are considering is the fundamental Gaussian mode. So now this is your Gaussian beam propagation. So now if this spherical mirrors is smaller in sizes, we lose the intensity. So that means you will not get a stable resonator for the Gaussian beam. So that is what we require to have. Your beam size will be smaller than your mirrors, or your mirrors are larger than your beam size at the position of the mirrors. Okay, so now we consider the other resonator, so that is plane mirror with the spherical mirror resonator. So this is the one, your M1 and M2, which are having a radius of curvatures infinity for the plane mirror and L for the R2. So they are separated by distance L, and they position Z equals 0 and Z equals L. So we are going to find the Gaussian mode of the resonator. So Gaussian mode must have a radius of the curvature equal to the mirrors at the position of the mirrors. So that means the Gaussian mode having a radius of curvature at this mirror will be same as this mirror curvature, and the radius of the curvature of the Gaussian mode at this mirror will be same as of this mirror radius of curvature. So that means, as you see now, because your mirror has infinity, your R1 equals infinity, now you see the radius of curvature for the Gaussian mode also infinity. Now as you go towards the mirror size, you will get the Gaussian mode curvature will be similar or equal to the radius of the curvature of the spherical mirror. So now, so the Gaussian mode radius of the curvature at its width position is infinite. We already know that in our previous session. Your Gaussian mode radius of the curvature at the beam width always a plane wave. So that means its radius of the curvature is infinity. So that means in this configuration, so this is our Gaussian mode we have discussed in our previous classes. This is our Gaussian beam at Z equals 0. That means at the focal spot you have a beam width. So at the beam width, your plane mirror, your wave is plane wave, and the radius of curvature is infinity. So now in this case, in the sense we have plane mirror and spherical mirror resonator, your Gaussian mode must have its width at the plane mirror. That means that, as you see, the radius of curvature of this our Gaussian mode infinite at the plane mirror, that means that the beam width has to be at the plane mirror. So now we recall the equations from our Gaussian beam lectures. Your W naught, your beam width radius, that is equals to lambda z naught by pi whole for 1 by 2, and your r of z, that means the radius of curvature at z, that means at a different position of g direction, that equals to z into z plus z naught by z whole square, where z naught is your Rayleigh range parameter. So now your r of z, so I want to calculate r of z, that is equals to L. The reason is r of z at z equals to 0 is infinity, that is our beam width position. So now I want to measure what is the size of the beam width. I want to measure W naught size. To measure that, I will take your r of z at position z equals to L, that can be substituted in this formula. So z equals to L, that means your R2 equals to L into 1 plus z naught by z whole square. So now from this equation we can get z naught. So that means z naught equals to, this square root becomes square to the W naught square. So lambda z naught by pi equals to W naught square. So now z naught equals to, you send this side, pi W naught square by lambda. So now I am going to substitute z naught. So this is the way you generally calculate your Rayleigh range, because W naught you can experimentally find out. So using different techniques you can find out your W naught. So that is your beam width. Okay. So now from this beam width you can calculate Z naught, because you know what is the wavelength of light you are using experimentally, and you can measure W naught using different techniques. One of the technique is a knife edge experiment. Using knife edge experiment you can calculate your W naught. So now pi is constant, from that you can get Z naught. So in this case now you substitute your Z naught in this equation. So now your R2 becomes L into 1 plus pi omega naught square by lambda L whole square. Okay. So now your R2 equals to this equation. So now I am squaring whole term. So this becomes pi square omega naught square, or W naught for 4, because W naught square into square, or all whole power square, that becomes W naught for 4 lambda square and L square. From this you can able to extract W naught. You can get W naught, if you solve this equation you will get W naught equals to lambda L by pi whole power 1 by 2. So because you see it has square term, these pi, lambda and all are square terms, we need 4 terms, so it will get root of lambda L by pi, and your R by L. So because I am taking R2 as a R, so that is an L, this doesn't have any powers, so that will get whole power 1 by 4. So you solve this one, you will get W naught equals to lambda L by pi whole power 1 by 2, R by L minus 1 whole power 1 by 4. So this gives the Gaussian mode of the resonator. So now we know what is the spot size. Okay. So now we know what is the spot size of our Gaussian beam. So this is our Gaussian mode spot size, because we are calculating for the Gaussian mode. For example, if L is greater than R, in this condition your L is greater than R, what does it mean? Your R2 is smaller compared to the length between length of your resonator. So your R here represents R2, the radius of curvature of your spherical mirror, because the radius of curvature of your plane mirror is infinity. So I am treating R as your R2. Okay, now you see your L is much greater than, what happens? This becomes a negative term. as your 1 by L is increasing, these terms have less prominent than the second term. So that becomes your W naught becomes complex. When your beam width is complex, your fundamental mode, that is your Gaussian mode, becomes complex. So now what happens? This cannot sustain in the cavity. So this cavity can be a unstable cavity for the Gaussian mode. Okay, so as we see, your L cannot exceed that means your length of the cavity cannot be exceed your radius of curvature of this spherical mirror in this resonator configuration. So in that case, this resonator, in this condition, this resonator behaves as a unstable resonator. So now by increasing your R, keeping the L is fixed, we can increase the W naught. So that, see, now your W naught, because we know the fixed wavelength, because your wavelength is fixed what you required, and now how you increase your beam width of that particular wavelength is depending upon your R. If you increase your radius of curvature of the mirror M2 in this configuration, you can get bigger beam width. So the reason we require bigger beam width, because if your beam width is high, that means the volume which can interact with the lasing medium will be higher. So that means this mode in this cavity increases the interaction with the amplifying medium. So the high power lasers, one must have this condition. So this, to get the once what he called this volume of the region of this mode, he called mode volume. Your W naught, your spot size. So in 3 dimension we can call it's a volume of the region, that is your mode volume. Once your mode volume is higher, so that means you have more interaction with the amplifying medium. When you have more interaction, you expect more power. So that is the reason for high power lasers, this is one of the condition that you must have higher or larger cavity mode volume. Okay, so now I am going to consider a spherical resonator. So that is a Gaussian mode in a general spherical resonator. So what is meant by general spherical resonator means, now I don't know what is radius of curvature R1 and I don't know what is the radius of curvature R2. From this I want to get the stable condition for in general using 2 mirrors. Okay, so those 2 mirrors are I am taking as a spherical mirrors. You can say that your plane mirror is the extreme condition of your spherical mirror. So you know that your radius of curvature is infinity and your radius of curvature is large, like this is small one. So I am taking the range of from R equals to infinity to the max small as I can. So this is whole range I am going to cover in this general spherical resonator. Okay, so now this is my general spherical resonator, and right now this beam width is not at the center, at some arbitrary position in between. Okay, so now this position or at Z equals to Z1, so now the position of the mirror M1 at Z equals to Z1 and M2 will be Z equals to Z2. That means that the beam is propagating along Z direction. So these mirrors at the certain positions Z1 and Z2. So now we recall the equation, your R of Z equals to Z into 1 plus pi square omega naught power 4 lambda square Z square. So now I substitute R of Z1, that means I want to know the radius of curvature of the mirror M1. So this is the radius of curvature of the M1, and similarly the radius of curvature of M2 becomes at Z2 position, it has to be Z2. So there is a typo here. R of Z2 equals to Z2 into 1 plus pi square omega power 4 lambda square Z2 square. So I will define the k square as pi square omega now power 4 lambda square z square. So k1 square means for this whole factor, k2 square means this whole factor. Okay, so I am choosing the sign conversion that R is positive towards the resonator. So for example, if my concave surface towards right now I am going in this direction, if I see the concave surface, so this becomes a positive and this becomes negative. So this is the sign conversion as how you see from your laser resonator. So when you going through towards the laser resonator, which have a convex and concave surface, that becomes a positive. This is I am choosing a sign conversion. So that means your R of Z2 equals to R2. Okay, your R of Z2 equals to R2 and R of Z1 becomes minus R1. Then I am going to substitute your minus R1 equals to, so R of Z1 equals to minus R1. So minus R1 equals to Z1 plus this whole term is considered as K1 square. So Z1 plus K1 square by Z1. So because I am bringing Z1 into the bracket, so this Z1 gets, one of the Z1 gets cancelled. So you will get this one. And similarly, R of Z2 equals to Z2 plus K2 square by Z2. So this is the radius of curvatures of the mirrors. Okay, I will stop here.